Hello, this is Rick from Bike Fitness Coaching. We're going to have a continuation of our Bike Fitting 101 series, how to choose the correct crank length. This is how we did it. We chose the correct crank length via a biomechanical bike fit, fitting to safe joint angles, not fitting with pain as the end result. Fit in the middle of the safe range, then fine-tune for maximum comfort and or performance. This is how the bike fits used to be back in the 60s and 70s and 80s. Long 180 cranks, jamming the knee, putting extra pressure and shear and compressive forces on the knee. This bike looks a little small for the rider. This looks like this rider could use a bike fit. The cranks or the saddle could be too low. This looks pretty good. This person looks really good on the bike. Just some examples. But first, some terms. Most in the bicycling industry are using the term short cranks. What is really a short cranks? When 180 cranks used to be the standard, 175s used to be considered short. When 175s used to became the standard, 172.5s were short. When 172.5s became the standard, 170s were short. I think a better term is right size cranks, because every individual will have a different length crank based on their anatomy. So let's use this new term going forward. So first, our belief as a bike fitter, it's mandatory to learn how the knee actually works. This will help us understand where the stresses are to the knee along the pedal stroke. So how do we do this? So to do this, we need to know and learn human anatomy, which is the study of the structures of the human body. With respect to cycling, we've got to learn what and where and how the greater trochanter works, the femur, tibia, patella, patellofemoral head, articular cartilage, meniscus, lateral malleolus, ACL, PCL, MCL, LCL, tibial tuberosity, metatarsals, lateral and medial longitudinal arches, transverse arch, sesamoid bones, etc. There's a lot to knowing the human anatomy with respect to cycling. Kinesiology, the study of human movement, and biomechanics. This is a big one. So mechanics versus biomechanics. Bike fitting is a process of adjusting a bicycle to fit a cyclist. The term mechanics about the bike and biomechanics about the body refer to two different aspects of this process. One of the issues is most scientific studies are based on mechanics, not biomechanics. There are numerous scientific studies that have investigated the impact of crank arm length on fatigue and cycling performance. Factors like power output, energy expenditure, oxygen consumption, and breathing. Well, the problem is that these studies should look at how these factors from a biomechanical point of view, not a mechanical point of view. For example, turning a crank is much more efficient when using a motor versus turning a crank via the human body, which needs to convert linear motion to angular motion, which is not as efficient. So why do these studies continue to consider the human body as a mechanical machine versus a biomechanical machine with its inherent range of motion limitations, which you don't normally have on a mechanical machine? Leverage and fulcrum in biomechanics. In the human body, levers are formed by bones, joints, and muscles. The fulcrum is the joint that allows movement. Here is the human leg. Here is the fulcrum, right at the back of the knee. There are three classes of levers. In bicycling, the legs function as a second-class lever, which means that the load is positioned between the fulcrum and the effort, which allows for movement when the knee is bent. As you can see, the longer the cranks, the more the knee is bent at 12 o'clock, which results in more shear and compressive forces placed on the patella and patellofemoral head, abrading away the knee's articular cartilage. More terms, mathematics and physics. Vector forces, aka force vector. A force vector is a mathematical representation of a force that includes both the magnitude, size, and direction of the force acting on an object. The resultant force of two forces can be found by adding the vectors that represent the forces. In this case, vector A, vector C. The resultant force is vector B, which is the addition of A and C. Most studies determine the shear and compressive force in newtons at the patellofemoral joint at different crank angles, not from studying forces via different crank lengths. What I mean by that is that if you look at most scientific studies for determining strains and strain gauges and forces, they take a set crank length and measure the force at the knee at each point along the measurement. They don't vary the crank length to determine if this adds or subtracts from the total vector forces of the resultant force. Another way to look at it, in the black, is the knee more relaxed as you would be maybe standing. The vector forces are pretty even. If you look at red, the more you bend the knee, the more quadricep force is applied, especially at the top of the pedal stroke. And when you, force 2 is basically at the tibial tuberosity. That stays pretty constant, but the resultant force is the addition. So you can see here the resultant force compared to this resultant force the more you bend the knee. Also, we need to know is how the muscle fibers actually work. So you need to look up sarcomeres, sliding filament theory. And why is all this important? Because muscles are most effective when they are in the mid-range of their movement than at their extremes, as this is when they are under the greatest tension. The mid-range allows for optimal recruitment of motor units, which is essential for muscle growth and strength. At the extremes of movement, such as fully contracted or fully shortened, the muscle is not under the greatest tension, which can hinder its effectiveness. Therefore, for optimal muscle performance and growth, it is recommended to focus on cycling in the mid-range of the movement of the legs. This can be accomplished by using shorter cranks, or the right size cranks, to put the athlete into the optimal power position. You can think of a squat, which is easier if you're doing a 200-pound squat. Is it easier to go all the way down and touch your butt to the ground and then try to stand up, or if you do eighth or even quarter squats? You can do much more because of physics and leverage that we already talked about. You can do more weight with less bending of the knees, and that applies directly to cycling as well and crank lengths. So this is how we have determined correct or safe crank lengths for individuals. Step 1, extract data. We're talking about height, crank length, inseam, type of bike, rotor tri, severity of pain, and other things you can look at. From thousands of bike fits we've done, then categorized by knee flexion angles into a given angle. Less than this angle, everybody had knee pain. From this angle to this angle, some had knee pain, some did not. Greater than this angle, no one had knee pain. Step 2, using linear regression, plot these data points and determine a formula. So what we did is we plotted the data points using linear regression and came up with formulas: low, mid-range, and high. From your formulas, then you can determine correct crank lengths for all height and inseam lengths. And we received these. I did some studies and found a lot of studies published by the US government on height versus inseam. And then we took the height, feet, inches, and centimeters, did the inseam, crank arm length, low, medium, high, based on these formulas, and came up with recommended crank arm lengths at these foot inches / centimeters and or inseam. And so far over The last 15 years we've been doing this, we've been pretty spot on. These formulas have proven themselves time and time again. And we do teach this in our bike fitting class. And like we said, we've done this process over the last 12 to 15 years, and all of our numbers have been validated over and over. If you have any questions, let us know, and hope this helps you determine your own safe crank ranges for your athletes. Thank you.